So today's topics are as follows. First, we'll derive transverse shear stress expression, which is this, for symmetric members. And then we'll apply the formula to simple cross-sectional shape example problems. And then we'll discuss about variation of tau xy along z-axis. Yeah, z-axis is the axis out of this plane. Okay, so let's begin from the first topic, which is derivation of this famous textbook expression regarding shear stress out of shear force V. So before talking about the mathematical derivation, let's think about some thought experiments. Suppose that we have a stack of like a thin films or thin wood piles. Then if you first you prepare this wood pile by gluing every interface like this, and then you do this push at the tip of this beam. And then in the second case, you don't apply any glue and try to apply force at the end of this beam. Then what you can expect is that if there is no glue, you see each plate would slide each other. However, for the glued wood pile, what you're gonna expect is there's gonna be no slide. Okay, so like this is the case with constraint, and this is the case without constraint. And if you imagine this whole beam, then what you can imagine is along that interfacial direction, along the x direction, you expect that there must be some sort of shearing stress and shearing force working on, right, to sustain this kind of as a whole beam under the bending. You need some sort of shear force. Okay, so for a beam under bending deformation, there should be non-zero tau yx, which is force on y surface along x direction. This is the definition of yx in our textbook when it's deflected. Okay, so this is something you can intuitively think about the stress distribution of a beam under bending, right? When you consider a beam under this bending deformation, what you can expect is to sustain this interfacial without any slip. You need some sort of a force from this third experiment. This is what you can realize, and then that exact shear force is originated from this shear force V. Okay, so let's try to derive the mathematical expression out of this third experiments. Of course, if you somehow obtain this tau yx, which is force in that direction or stress in that direction, then out of this mechanical equilibrium condition, tau yx equals to be tau xy. You can obtain tau xy, which is distribution over the cross section. Okay, so let's try to derive. So the first simple example you can imagine would be something like this. You have a simple cantilevered beam, and you have 1 point downward force at the right end of the beam. And if you draw the shear force diagram, it will be constant over the entire beam location. Then out of this, what about the tau xy distribution? So let's try to draw free body diagram, and let's use our classical divide and conquer method. So this is the front view of the beam. This is cross-sectional view of the beam. Okay, so there is you're gonna expect front view over left and cross-section view over right, and we are looking at exactly same cross-section. So for the front view, when making free body diagram, let's take infinitesimal length delta x and take this area, and out of this slice, let's take this red volume only in final consideration. So first, out of this slice, this slice with length delta x, this is the reaction you can expect. The beam on the beam, you have not only the non-zero shear force, you have non-zero moment. Okay, of course, moment becomes zero at this free end. So in this slide, you have left side and right side force and moment. Okay, of course, left side and right side force and moment would be different because you have like a distance delta x. At least for this specific problem, v and v delta plus delta v will be same. But if you consider general case, v and v plus delta v will not be equal to each other. Okay. Anyway, this is the front view, and regarding the cross-sectional view, let's think about where how the force distribution should be. So if you look at this top surface, you see that even though you have some surface, and through this surface you can have some sort of interaction over the shearing force and normal force. However, over the top surface it's completely free. So what you can expect is over the top surface there is no normal stress and no shear stress. So because there is no shear stress and no normal stress, and what you can expect is tau yx equals to be 0, which means that tau xy is also 0 at the top. Okay, so this is one thing you can realize out of this simple diagram. After we draw free body diagram for this slide, now let's focus on this red block only. Okay, so out of this red block, what you're gonna consider is force equilibrium along the x direction. So because v plus delta v and v is force along the y direction, we don't need to worry about it. So what you can expect is we have x direction force from the m, and we have x direction force and stress out of m plus delta m from right side. And in addition to this left and right side stress due to m and m plus delta m, we have shear force along this interface. Okay, so this is as what we discussed in previous page, right? So by combining stress from sigma L and integrating over the left surface, stress sigma R integrated over right surface, and if you also consider sum of shear force on the entire bottom of this red block, and if you look at if you change the viewing angle for this red block, and if you look at the bottom, this is your eye, you look at the bottom, the direction of delta H should be along the x direction. Okay, so by combining sigma L, sigma R, and delta H contribution, you have to consider force equilibrium. And here what you're going to be careful is this has dimension of stress, this has dimension of force, so you got to be careful. So out of this mechanical equilibrium along x direction consideration, so this is what you have to do. So when you do integration over sigma L, you should not do integration over the entire cross section, because you are considering this red block, and you are interested in this shear force delta H at y position. Okay, this shear force has different value at different y value, because you can see that as you change the size of your red block, you're gonna have different distribution of sigma L stress and sigma R stress. Okay, so you can imagine that delta H would be function of y. So when you do the integration, because our area of interest is this much, you have to do integration over the area which is larger than y point. Here I take this variable as y tilde because I want to say y as a fixed point, because I'm interested in shear force at fixed point y. So for the left side, you need x direction force from the sigma L. For the right side, you have x direction force sigma R, and you have delta H, which is force at the bottom, and this is left side, right side force, and this is bottom side force, and they have to be summed up to be 0. Of course, as I told you, at the top we have 0 force. So for the left and for the right, we have of course different sign here. So for the sigma R, when m is positive, you want to have like negative x direction force sigma R, or compressive negative x direction force. Regarding like a L direction, you have like a positive R direction for positive M. So this is something you gotta be careful about writing this expression. So for the left side and for the right side, yeah, be careful about positive sign here, be careful about negative sign here, and you have delta H, which is the bottom surface force, bottom surface shear force, and they have to be summed up to be 0. Now what you can realize is you have M here, you have M here, so contribution of M will cancel out each other. So what you're gonna left with is you have negative y tilde delta M contribution. And because we are considering quite small distance delta L and delta X, suppose that delta M is just constant over the entire cross section. So you put delta M out of this integral, you have I out of integral, which is constant. You only have y tilde dA, and you have to integrate this y tilde over the y tilde is larger than y region. Okay, and you have to, after this is a summation of first and second term, and if you add the final term, it must be 0. Now the problem is almost done. Let's define shear force per unit area as Q. Yeah, this is when you have shear force delta H, and this is your length delta X. Delta H, delta X will be meaningful number, because when you take like a larger slice delta X prime, you're gonna need like a different force, because you're gonna have different ML and MR due to different locations. Okay, so Q can be considered sort of normalized shear stress, shear force per unit length. And if you define Q as delta H over this slice with delta X, then if you massage this equation, what you're gonna get is delta H equals to be, if you take this equation to the right hand side, positive delta M over I and integral, and if you divide the delta X further, this is what you're gonna get about shear force per unit length. Okay, shear force per unit length is delta H divided by delta X. Now when you look at this delta M over delta X, when you consider delta X goes to 0 limit, it means that this first term becomes V, which is dm over dx. So you can arrive the expression that Q equals to be V over I. This is V and this is I, and integral and this integral is named as QY integral in our textbook. Okay, so this is the derivation of shear force per unit length. Now after obtaining the shear force per unit length, suppose that you have delta H force for entire bottom surface, and you have delta X, you have Ty. So the area of the bottom surface is delta X and Ty, and the force for entire bottom surface is delta X. So delta X divided by A bottom will be tau Yx for bottom surface. Okay, so the tau Yx average, because you can think about quite wide width Ty, and for that case tau Yx can be function of g. So if you consider average over the entire g direction, then what you can expect is delta H over delta X multiplied by Ty. This is width, and this is the A bottom. Then you can define shear stress, and shear stress turns out to be Q, which is delta H over delta X divided by Ty, and it turns out to be VQ over IT. Okay, of course Q and T is function of position, because if you think about like an I-beam kind of shape, your depending on your Y, Ty can be large here, Ty can be small here, so you're gonna have different thickness T. And regarding Q, when you take Y here, it will be your Q integral. When you take Y here, your Q integral will include a much larger cross-sectional area. Okay, and from tau yx equals to be tau xy, you can also equate tau yx average with tau xy average. So with this you can derive the expression for shear stress distribution out of shear force V and area moment of inertia, and Q integral, which is dependent on y, and thickness T, which is dependent on y also. Okay,